We're beginning Unit 5 in our study on probability. And this unit deals with probability distributions, and specifically discrete probability distributions. I'm Mr. Jackson.
And I'm Miss Hughes.
And to begin in talking about distributions, we're going to talk about probability distributions that are uniform in nature. So really, when we look at probability distributions, we should probably define what we're actually talking about.
Yeah.
When we talk about a distribution and what that means.
Well, and we've been doing probabilities. We've been calculating probabilities for particular events and particular outcomes. Right? What's the probability of getting this kind of hand in your next poker game? What's the probability of getting this kind of outcome for your committee? But a probability distribution is all possible probabilities for every possible outcome for your experiment. So you calculate every single possible outcome, and the distribution can either be shown as a table where you have the outcomes listed and then the probabilities next to them, or as a graph. And you're familiar with bar graphs and histograms and things like that, and so you can visualize the probabilities as being bar heights versus the random variable, so different outcomes would be along your x-axis, and the bar heights would represent the probabilities. The higher the bar, the greater the probability.
Okay, and that's for every single outcome.
Yeah.
So in any probability experiment, we need to define a random variable, right, which has a single value for the outcomes in the experiment. So in an example, we might be looking at, say, the random variable f, capital F here, which is the face-up number displayed on a standard die. Right? And so every single outcome for the random variable f is denoted as a lowercase letter that corresponds to, of course, the uppercase for the random variable. So here we have little f. So really, uppercase F defines the random variable that we're going to measure, while lowercase f defines the individual values. Okay, so let's take a look. We're going to stick with this dice example. And so if we look at the probability distribution for f, which is the upward facing value on a standard die.
Yep.
The random variable in f, so we've said it's little f. We could have, of course, 1, a 2, a 3, a 4, a 5, or a 6.
Notice that we've listed every single possible outcome in this experiment. And each one of those, so when little f equals 1, or little f equals 2, little f equals 3, each of those is a different outcome, and it relates back to the capital F, which is just face-up numbers in general.
Yeah. So here we can actually also define probabilities for each of these, and of course the probability of getting a 1 would be 1 in 6. And the probability of getting a 2, a 3, a 4, they're all the same probabilities. And so this is what we talk about when we say a uniform probability distribution, where everything has the same probability.
Yeah.
Okay. Here it is on, of course, the right-hand side of your note. Here is the graphical display, right, in chart form of the distribution. And we can see it's a bar. All the bars have exactly the same height because they all have the same probabilities.
Yeah. And again, your x variable is the random variable f, which takes on different values. And then your probability, your y-axis, is just, all the probabilities of each of those. And again, these are two different ways of showing a distribution. So recall, a distribution is calculating the probabilities for every possible outcome. And you can either show it in a table or in a graph or both.
We can make note of the fact, and this should be a reminder to us, is that if we sum up all of the probabilities, the probability of every single outcome, and we add them all together, we get a value of 1, right? So the probability that you roll a dice and you get either a 1, a 2, a 3, a 4, a 5, or a 6 is 100%. You are going to get something when you roll a dice. Yeah. And of course, what we can say about this is that this is nothing different than when we were using 1 minus the probability of A to find the complement, right? So the sum of all probabilities in any experiment is going to be 1, and here we're actually going to use that fact.
Yeah.
To reiterate, if all the probabilities in a distribution are equally likely, we call it a uniform probability distribution.
Yeah.
And it's one of 4 different types
that we're going to look at
in this unit.
Yeah.
So how do we find the probability, these individual probabilities? Well, if they're all equally likely, then the probability of any value x is just 1 over n, where n's the number of possible outcomes in the experiment.
Yeah.
Okay.
All right, so now let's talk about those random variables, because we defined, a random variable, capital F, as being the face-up value on a die, and then each value that could take on, we prescribe little f for that. And so most times the random variables, just to make life easy, are defined as capital X or capital Y.
Mm-hmm.
And then that way the probability of little x, the probability that little x equals 1, is just easier. You're more familiar with x's and y's. The random variables themselves, however you choose to define them for your convenience, they can either be discrete or continuous. And so recall that discrete variables can only take on specific values, and often they're usually integer values within a given range, while continuous variables can have an infinite number of possible values on a continuous interval. So those continuous variables, you might recall, you might liken them to variables where if you had a more and more sensitive measuring tool,
Mm-hmm.
you could go to more and more decimal places.
Mm-hmm.
And so those continuous variables have that infinite number of possible outcomes.
So here in example number 2, let's classify each of the following variables as discrete or continuous. So the number of phone calls that are made by a salesperson.
Okay, so could you make 1.23 phone calls if you were counting phone calls? What do you think, Mr. Brown?
No, I'd say the answer would be no. You can either make 1 phone call or 2 phone calls or 3 phone calls. So this would definitely be a discrete variable.
Yeah.
However, conversely, the length of time the salesperson spent on the phone,
that could be a continuous variable, because you could have an infinite number of possible values if you were going to an infinite number of decimal places there.
Yeah, so if we use a really sensitive watch to time how long this individual's on the phone, then we could go to more and more and more and more decimal places. Yeah. So the number of widgets sold by some company.
Well, you either sell the widget or you don't sell the widget. So I would say, again, it's got that feel that it's an integer value, like whole numbers or positive and negative integers. So we're going to say that one's discrete.
Mm-hmm. The distance from the Earth to the Sun. In fact, as the Earth goes around in its orbit, its distance from the Sun does change.
Yeah.
Because it's not a circular orbit. It's a little bit different.
And it doesn't jump to discrete measures. No. It doesn't jump exactly 1 more centimeter every time it goes around. So because we can measure that with more and more sensitive tools, again, we're going to say that's a continuous variable.
Yeah, exactly. Yep. All right, so enter into basically a new thought or a new idea, and it's called the expected value. And if you've ever watched Deal or No Deal, and you've watched that television show, that television game show, you'll notice that the banker always comes back with an offer. And interestingly enough, the offer that the banker gives is usually, and I wouldn't say usually, it's almost always a little bit less than the expected value for the prizes that remain. And so we're going to talk about expected values and what they're all about. In general, for a distribution, it's the predicted average of all the possible outcomes in a probability experiment.
Yeah.
Okay, so it's equal to the sum of the products of each outcome, right, with its probability.
Yeah.
So here's a definition. And we would say that basically the predicted average is the value that x has times its probability, plus the value of x2 times its probability, all the way down to the value of n times its probability. And of course we can recognize this as in summation notation, but really it's, when we talk about this, it's just the predicted average of all the different outcomes.
Yeah.
It's a little bit difficult to vision without the use of an example. So let's take a look at one right now.
Yeah, and in fact, I've done this a few times with students, and it helps them to consider that the expected value, so capital E, of capital X, right? So the
Mm-hmm.
expected value for your random variable, it's a weighted average.
Mm.
And we've done weighted averages where we know that, we take a value and we multiply it by its weight. And then we add that to the next value multiplied by its weight. So we're taking the average of values that have different weights, and the probabilities are the different weights.
Mm-hmm.
And so if it's more probable, it's going to get a greater weighting. You can also think of this expected value or this predicted average as the average if you were to run this experiment an infinite number of times and actually average all the outcomes. That's what your expectation is, or your expected value.
Okay.
And remember that we used to divide the sum of the weights times the values by the sum of the weights. But because all the probabilities add up to 1, we would just be dividing by 1. That's why you notice that there's no denominator in that formula, right? So think of it as a weighted average.
Okay.
Yeah.
So here's a simple game. Let's say you roll an even number, right? You get that number of points. So if you roll a 2, you get 2 points. If you roll a 4, you get 4 points. If you roll a 6. If you roll an odd number, you're going to lose that number of points.
So minus 1
So if you roll a 1, you're going to get minus 1 points. If you're going to roll a 3, you're going to get minus 3 points, and so on.
All right. And we would tally this up as we play.
Yeah. So let's set up a probability distribution of points in this game, and then calculate the expected value in the number of points per roll. We could even set this up. We could even change it and say, okay, if basically we roll a dice, if the number's even, you get 2 points. If the number's odd, like I get those points, right? Yeah. So even points you get, odd points I get. Doesn't matter. Either way you look at it, it's going to be the same thing. So,
and the question is this a fair game? Is there a 50-50 chance here, if we're adding up positives and negatives, for it to be even? We would think that when you add up all the positives and negatives, if it is even, it should come out to 0, right? Okay.
So here is the number on the upper face of the die. 1, 2, 3, 4, 5, and 6. So the number of points that you're going to get is -1 if you get a 1, +2 if you get a 2, -3 if you get a 3, and so on and so forth. Okay? This is a uniform probability distribution, so the probability of each of these is the same.
Yeah.
Okay? So the way that we go through this and the way that we solve to finally get an expectation value is we take the value of the random variable and multiply it by its probability. So here we'd get -1/6.
Yeah.
In the next line, we get 2 times a 6th. In the next line, we get this, and so on and so forth all the way down the list.
Notice we've just kept the denominators all the same for simplicity's sake, because now you're going to sum all these up, right? Because it's the sum of each variable times its probability, and it's easier to add them up when they all have the same denominator.
Yes, exactly.
Yeah.
So -1 + 2 plus -3 plus 4 plus -5 plus 6.
Yeah.
When you add all those up, you get 3 out of 6.
Yep.
Okay? So basically what this means is that the expected value is 0.5. So the expected number of points that you would get in this game would be 0.5.
So if you were to play this game for infinity,
at
your
the end
average,
of this,
you'd have 0.5 at the end. Like that would be your expected value. So then the question remains, is this a fair game? Well, since we're dealing with positives and negatives, in this particular case, to be a fair game, the expectation should have been 0, right? Because then the positives and negatives balance all out, and then it's just random chance. But you can see here that in this case, it's not really a fair game. It's biased towards that positive.
Towards
slightly.
that positive,
Yeah. And notice again that we've set up the probability distribution, and that word distribution means every single possible outcome. And we've done that with the table. And then we've just had a little adjunct onto the table for part B to calculate the expected value. We've just created a new column. And again, you can do this in Excel because you know how to use Excel for these kinds of things and these formulas. And you put in the values, and then you can autofill and use the sum function and everything else. So these distributions, when you're creating them as a table, can go pretty quickly in Excel.